We are talking about a power factor improvement. So this problem belongs to power factor improvement. A question is given in such a way that an installation is supplying the following loads. So what are the loads supplied by the installation? 300 kilowatts, right? So it is supplying 300 kilowatts at unity power factor, 1000 at a 0.9 power factor, 1500 at 0.8 power factor. As it is 0.9, they said lagging, 0.8 lagging. Okay. So with this given information, they are saying to find all these values. So first, let us find the first one. Total load. So what do you mean by total load? Means what is there on the overall system. So what did they say? They are having 300,000 plus 1500. So I will add that same. So 300 plus 1000 plus 1500 kilowatts. So our total is 2800 kilowatts. So our total load on the station is 2800 kilowatts. And we can say this as our real power because this is the actual power which is on the load on the station. So this is our real power. Next, second one, they are asking us to find the reactive power. So to find the reactive power, what does we say? So usually reactive power means the power which is in the system, which is calculated through the load on the system. And here the load on the system is given with a power factor. So as we don't know the actual reactive power, we can use the real power with a power factor. So they said 300, right? 300 kilowatts at unity power factor. Unity power factor means cos theta is 1. Cos theta is 1 means theta is cos inverse of 1. So I am saying 300 tan theta is the reactive power. So I am saying tan theta, but I don't know theta. I am writing it as cos inverse theta. Theta is how much? 1, because they said power factor is unity. So this is the first load. Then another load is 1000 kilowatts at 0.9. So I will say tan of cos inverse 0.9. Next, another load is 1500 at 0.8. So I will say tan of cos inverse 0.8. So if we calculate this, what is the value we are going to get? Will be our reactive power. So if you calculate this, you are going to get 1609.3, which is a reactive power. So we write it as kVAR, right? Next, third one. Third one is apparent power. So what is our apparent power? So according to the power triangle, we can say apparent power is nothing but square root of real power square plus reactive power square. So what is our real value? 2800 square, right? And reactive power is 1609.3 whole square. So if you calculate this, you will get 3229.53, which is our apparent power. Apparent power means kVAR the units, right? So kVAR. Then fourth one. Fourth one, they are talking about the power factor. So what is power factor? So power factor is cos theta is equals to real power by apparent power. So power factor is nothing but real by apparent. So what is our real value? 2800. What is our apparent? 3229.53. So if you calculate this, you will get 0.867. It means this is the lagging value because this is less than 1. So power factor is less than 1 for the power station. The overall power factor is less than 1 because of uneven loads. So now fifth one. What is the fifth one? They are saying that maximum unity power factor load to be supplied. So maximum unity power factor to get how much we should supply. So it is, so the maximum unity power factor can be supplied when total apparent power multiplied with unity power factor. So what is our apparent power? 3229.53 multiplied by 1. So 3229.53 kilowatts is the maximum load you can give to make unity power factor. So it means real power is 28, but we are giving 3229.53. If we give 3229.953 to make system a unity power factor, so that is the problem. Okay.